All right, it's 11:15. I think we'll get started. So don't forget about the homework, and the way to do homework problem number one, or the first homework, it's in the book. You'll have to read about that. You'll have to plot some things and look at the slope and intercept. I'm not going to cover that procedure exactly, but you do want to take a look at number one. It's going to take you a little time. There's some algebra to do. There's some plotting. You know, make sure that you use the XY plot in Excel, and then you can get the slope and intercept from the best fit line. But if you don't use an XY scatter plot and you try and use a line plot or something, it doesn't work out very well. So take a look at number one, start that soon. The second one's relatively easy. We've gone over that one, but you know, the first homework problem will take you a little time. Feel free to send me email. We'll do office hours, all that stuff. But that's just a lookout. Any other questions, comments, things people want to talk about before we get started? All right. So we really want to talk a little bit more, or we just want to, I want to review this solubility parameter delta, because solubility parameters are used a lot in polymers. You'll learn about them in your future polymer classes. There's different types of solubility parameters. There's Hansen solubility parameters. There's Hildebrand solubility parameters. Some people break down solubility parameters in terms of dispersion, polar component, hydrogen bonding. So there's a lot of depth in the solubility parameter as you move on in your career. But what you really need to remember for this class is that it's a way to figure out what the intermolecular interactions are when we talk about polymer solutions. And the way to remember that is that solubility parameter, which, you know, is kind of an esoteric name, but it tells you something about solubility, which is how we're going to use it, is derived from the cohesive energy density of what you're interested in. And the cohesive energy density of, let's say, A interacting with a bunch of other A's, so in some sort of condensed medium, like a liquid, like a solid, something like that, if you take all of those molecules and move them way apart so they don't interact, or you vaporize them, that's reflected in the heat of vaporization. And then we have this volumetric quantity, or the molar volume, so we get energy per volume for the cohesive energy density. And so we can derive the solubility parameter from that. And so the cohesive energy density is not the important part of this slide. It's the solubility parameter, and learning how to work with solubility parameters and what they mean, that's important. Great. And so when we think about the, if we know about the solubility parameter, and that tells us about the intermolecular interactions, remember that's going to go into something to do with delta H and eventually chi. So remember, the only thing that we're talking about in terms of Florey-Huggins, where intermolecular interactions are built in, is in the interaction parameter in chi, or we could use delta H if we're interested in that. And so it's the difference of these solubility parameters and the volume fractions that are important. And you know, if delta 1 equals delta 2, then delta H mixing contact equals 0. So we have equivalent intermolecular interactions. And this helps guide our, well, this is a quantitative understanding of the idea that like dissolves like, right? And so we look for similar solubility parameters to tell us about what polymers might be soluble in what solvents, or what solvents might be miscible with each other. And so we can look at this and say, okay, I think that toluene and ethyl acetate will actually form a homogeneous mixture. And so what's an inhomogeneous mixture? If we're just talking liquids, what's an inhomogeneous mixture that you know right off the top of your head? What liquids don't mix? Oil and water is a good one, right? And if you shake up, oil and water will phase separate based on their density. And if you shake it up really hard, what does oil and water look like? Cloudy, bubbles. You know, if you really shake it, it can look like a colloid. And so that gives us a good idea of what soluble polymers might look like when they're miscible with solvents. And so if we take what's a miscible solvent system, or what are two solvents that mix really easily that you know off the top of your head? Ethanol and water, right? It turns out, do we have ethanol on here? It turns out that ethanol and water form a homogeneous solution, but they have really different solubility parameters because solubility parameters are not good at capturing those intermolecular interactions. And so you always have to watch out for H bonding and other types of intermolecular interactions that might give you a soluble system when you can't anticipate it from the solubility parameters. But we can use this table to say, okay, you know, if I have polystyrene and I want to form a nice solution with polystyrene, I'm going to pick something like toluene because they have similar chemical structures, similar solubility parameters. You know, if I try and take Teflon, which is PTFE, and dissolve it in toluene, I'm probably not going to have a lot of success, right? I'm going to get an immiscible or a non-mixed system based on the insights from the solubility parameter analysis. So this is how we can use these tables practically, and there's lots of tables of solubility parameters out there because this is the #1 way to calculate the Flory-Huggins interaction parameter. Any questions on that? Any confusion about solubility parameters?
I was just wondering, so does this not take into account like polarity and stuff, so like polar and non-polar molecules?
It takes into account non-polar interactions, but it doesn't do a good job at capturing interactions between a polar molecule and a non-polar molecule. And so we get that right from the idea of water and ethanol. We know those are miscible, but look, they've got, let's see, 11 times or 11 points different solubility parameter. We would say under usual circumstances, there's no way that's going to work. And of course it does because they hydrogen bond. And so what I'm saying is that this table works for non-polar molecules, when you have dispersion interactions, things like that. It doesn't work for some exceptional cases where there's hydrogen bonding. Yeah, because you know we could put another really polar solvent on here like dimethyl formamide, and I think the solubility parameter of DMF is something like 30, and there's water and DMF are miscible because they're both really polar, and so we know that they'll be miscible. But this table wouldn't predict that something like polyvinyl acetate is also soluble in DMF. So it misses the really polar solvents. And that's why there are other types of solubility parameters that you'll study in the future, Hildebrand solubility parameters and other things like that, that try and build those interactions in. But for the simple cases that we're starting with, we could just go off the table when we remember the one exception. Is that cool?
Yeah.
Cool. Any other questions on this? So you're going to have to use solubility parameters to figure out stuff is what I'm saying. And the one thing to remember, and we practiced this yesterday or 2 days ago in lecture, practice this on the homework, is that we can use group contribution theory as we did in this example. If we don't know the solubility parameter, or if it's not in the table, we can make a calculation of what the solubility parameter might be based on all the different groups. And so you have to piece the molecule, or in this case, the repeat unit together from its different contributions. All right. Yeah. So this is a really important slide. So we've been building up in terms of how solubility is related to the cohesive energy density. It incorporates these intermolecular interactions in the mixing. We already handled the entropy, right? The entropy is just based on the configurational part, or the way that we can arrange all the molecules. But delta S, the way we approached it at the start of this section, doesn't tell us about the intermolecular interactions. And so this now is going to be really important in terms of the Flory-Huggins interaction parameter and how we calculate that based on the volume or the molar volume of the solvent and the two solubility parameters that we're interested in. So that's where we build in intermolecular interactions. Because there's no intermolecular interactions in this term and none in that term, right? Those are just the volume fraction of polymer and solvent. So this is important to remember because we use Flory-Huggins theory over and over and over to describe mixing of polymers. Any questions on that? All right, let's see, what do we have next? All right, so I think we covered that last time. That one's easy. So if the difference in solubility parameter increases, we have poorer. The solvent is not as good for your polymer. We know that delta G mixing is going up, right? So if we increase delta G of mixing, if it's getting closer to zero or it's getting further away from zero, we know we have a poor solvent system for our polymer. This really doesn't tell us whether it's positive or negative, but if the Flory parameter increases or those two deltas, delta 1 and delta 2, get further away from one another, we have a poor solvent system for our polymer. Okay. This is a good question, so you can get out your clickers. And I did check, this room is still on CD, or at least the box is picking up CD. Everyone's covered. And so if we increase the difference in solubility parameters, and we can just add between, let me get rid of that, between polymer and solvent, how would we expect the conformation of the polymer to change? So the conformation is describing the idea that how big is this coil? Is it an expanded coil? Is it a collapsed coil? I know we have more than 27 people in here, so you can get organized. I'll leave it up for a little while. And so we know that if we increase the difference in solubility parameters, is the solvent getting worse or better for the polymer? Worse. So the further the difference between solubility parameters, the worse and worse the solvent is getting. And as the solvent gets worse for the polymer wants to associate more with itself, and the solvent wants to associate more with itself, and they don't want to associate with each other. So what does that do to the conformation? So if you have more polymer-polymer contacts and less polymer-solvent contacts, what happens? Ah, great, 54, that's a good number. And so we know the polymer becomes more coiled as the solvent becomes a poorer and poorer solvent for the polymer. And this is the gist of the questions I'm going to ask. You know, is it miscible, or does the polymer want to dissolve in that solvent? So make sure you know what miscible and immiscible mean. And we'll talk about how the conformation changes depending on whether the solvent is better or worse for the polymer chain. And eventually, as I said at the bottom, if the solubility parameter is different enough, we would get phase separation. So we get either liquid-liquid phase separation with the polymer rich and a polymer poor phase, or we would just get polymer precipitating out a solution and we would get some sort of milky colloid or something like that. The issue with solubility parameters is we don't know what that difference is for immiscibility. Is it 0.5 in solubility parameter? Is it 1? Is it 3? You know, we could probably bet it's like 10 if we ignore hydrogen bonding, but we don't have a quantitative measure of the solubility parameter needs to be this, and then it becomes immiscible. So that's something to remember. Any questions or comments on that? All right, so that's why we study conformations first before we talk about this. And so now we have a quantitative description of what the end-to-end distance is like using random walk model or the freely rotating chain or the valence angle model, etc. And now using solubility parameters, we have a way to describe what's going to happen to that coil. And you'll continue to put this together in your future classes. All right. So one really cool soluble system are polyelectrolytes. And so we're going to talk about polyelectrolytes. They're really interesting. They're very useful. And polymers similar to this are now used in batteries, fuel cells, solar cells, things like that. So polymers that don't have any ions on them. So if you look at polystyrene, is polystyrene hydrophilic or hydrophobic? What do you think? Hydrophobic, right? It's just a piece of plastic. It's useful for structural stuff. We make wedding champagne cups out of it, safety glasses, or other technological styrofoam, structural things, right? It's hydrophobic, stands up to environmental stress. That's both good and bad because we get a lot of plastic waste that way. Polyelectrolytes. What's an electrolyte? So what's the scientific definition of an electrolyte? Bless you. When they say get your electrolytes after you work out, what are you doing? Ions. Electrolytes equals ions. All they're doing in that Gatorade is just pouring in a little sodium chloride and then coloring it and selling it to you. And so electrolytes are ions, right? Your body needs ions to do signaling and all the things that are miraculous in living systems. But we can make polyelectrolytes, which in essence are polymerized ions. And so you see this sodium charge here, and that sodium is connected to this monomer. It's actually connected to the whole backbone, but this is an acrylate group. Let me redraw that just so no polymer people get mad at me. So the monomer for this is, let's see, we have double bond, carbon here, carbonyl, oxygen minus, Na plus. So this is sodium acrylate. And we can make sodium polyacrylate by polymerizing this thing using our vinyl polymerization, because this thing is just all the same as R. So that's cool. Now we have a way to make polymers. Is this thing hydrophilic or hydrophobic, do you think? It's hydrophilic. Electrolytes in general are hydrophilic unless they're insoluble salts. But this thing is soluble. Sodium makes things, let me move that. Sodium makes things really soluble. And so there's not a good spot for that right now. There we go. But we can make hydrophilic polymers that have ions on them. And that's really cool because there's lots of interesting things that happen. When we put this polymer in water and it's hydrophilic, what happens to the ionic groups? They just float apart, just like sodium chloride would do. But instead of the chloride floating away as an atom, it's all tied to a polymer. And we'll see what that picture looks like. So there are counter ions. And the counter ions, in this case, are sodium. They're always the free ion. So you can call this, what is the free ion or what is the counter ion? That's sodium. The polymer backbone is charged. Sorry for that typo. And so that's interesting. We'll talk about what happens when this sodium charge floats away from the backbone. And then we'll talk about some interesting properties like osmotic pressure and other properties of electrolytes. So this is a totally different polymer structure than we've seen before. We haven't seen any polyelectrolytes. We haven't seen any polymers that do dissociation, nothing like that so far. We haven't studied many water-soluble polymers except for maybe polyethylene oxide and polyvinyl alcohol, but those are non-ionic. They're just really strongly hydrogen bonding, right? Okay, so a new type of polymer, but it's worth talking about that. So we just want to make sure that we're up on what happens when we put electrolytes in water. And so in this situation, let's say we have a semi-permeable membrane or some separator between two different compartments in pure water. What is the delta G of this system? Zero. It's at equilibrium. So this is at equilibrium. Why is it at equilibrium? What causes this system to be at equilibrium? The chemical potential of water on both sides of the membrane is equal, right? That's the definition of equilibrium, or we can say the concentration of water on both sides of the membrane is equal. So that's concentration is an approximation of chemical potential, but formally, remember when you did all those mu1, mu2, chemical potential is the same on each side of the membrane, right? Equilibrium. Nothing's happening except for Brownian motion, self-diffusion, molecular motions, all of that stuff. Okay, we're going to put in some sort of solute into one side of the tube here. And so what happens is now the water concentration is lower on the solute side because you've added other stuff, right? In this case, I think that's glucose or whatever it is on one side. And so the concentration of water on this side is higher. And this is set up with a membrane, so our glucose can't diffuse through the membrane to equalize the concentration of glucose on both sides, and we go back to equilibrium. And so water moves from the high concentration side of water to the low concentration side. And in this setup, it moves towards the solvent. What do we call diffusion of water? Osmosis. That's right. And so you've all heard of reverse osmosis membranes. Basically, reverse osmosis is making water go from low concentration in salty water to high concentration in pure water. That's why it's called reverse osmosis. But osmosis is just water diffusion. It's just a fancy name. It's an old term and it's stuck. So we have water diffusion from one side to the other because we have a negative delta G in the system, so it's gonna move because the water concentration or the chemical potential of water is not the same on both sides of this membrane. Okay, that's an important thing to understand, and we just need to all be square with why water moves the way it does, and we need to think about, okay, how is this system going to seek or approach equilibrium once we disturb it? Okay, so if we put a polyelectrolyte, so remember that example, we'll come back to it. We put a polyelectrolyte in solution, right? This is our garden variety polymer coil. And this is what it looks like when we first dump it in, like the first instant where we still have the ions stuck to each other, or we have pairs of ions because positive charges can't live without negative charges in a charge balance system without electric field on it or other tricks. And so what happens when we put this in water, there we go. Ions dissociate. But remember, the negative charges are stuck to the backbone, right? They can't go anywhere. And so they're stuck right on the backbone. That's what this drawing is trying to indicate. But the sodiums can float away, right? They're not stuck. They're fine dissociating from the acrylates, and so they float away. So what do we know about positive and negative charges? So if we take all the water away, the positive and negative charges are going to go together, right? So, if we don't have any water to solubilize that sodium, anions and cations will get together. And in this system, we have one sodium, one acrylate. But as soon as we put water in there and we dissociate the sodium away from the acrylate, now we have some distance between the sodium and the acrylate, but these charges can repel each other. So you need to think about what interactions the ions are going to have with their oppositely charged partners. And then because those negative charges are stuck on the backbone, there's the potential for interaction between charges that are stuck on the backbone. Because if you look, this picture is not perfect because there's a charge every every two carbons, right? You're going to have negative charge, negative charge, negative charge. And those charges are close enough together that you can get like charge repulsion. So you have ions dissociating, but you can have like charges repulse one another. And if those charges repulse one another and eventually they repulse one another enough, what's going to happen to the size of that coil? It's going to stretch out a little bit, right? So eventually this will cause a stretched or expanded coil. Sorry, that doesn't look perfect on the screen, but you could see it in the notes when you download them afterwards. So that's really interesting. That's the first time we've been able to really change the size of the coil, other than changing the solubility parameter of the solvent that we just talked about. But now the size of the coil can change depending on how much dissociation we get. What's one way? So we could take the water away and the ions reassociate. And when those ionic charges are really close together, we don't have much like charge repulsion because every anion has a cation. What's another way to decrease this like charge repulsion? Does anyone have an idea? So say we have a coil that looks like this, sodium polyacrylate sitting in water, and we say we want to make it a small coil again. What could we do? Does anyone have an idea? We could add more positives. That's a really good idea. What do those more positives do? They can neutralize the negative charges. But do you have a bucket of positive charges? No. What do you have a bucket of? Positive and negative charges, right? So you can add more salt. It's okay to put more negative charges in solution. So you can add salt to the bottom situation, more sodium chloride, and you can shrink that coil down, because if there's more positive charges around, you have less like charge repulsion. And I'll show some examples of that. But this idea of thinking about, okay, what's my situation in pure water? What does it look like? And then if I change something in the water, what happens to the ion pairing? That's a way to figure out what's going on with all the stuff we're going to talk about. Any questions on this? Like I said, this is worth thinking about because we use these super absorbent polymers right now. So they're used for all sorts of things like diapers, which is a really important multi-billion-dollar business. If you go work for Kimberly-Clark, they're very serious about diapers. Or it's used in environmental remediation because they suck up a lot of ions. And also these types of polymers are used in batteries, fuel cells, other things like that. And so it's worthwhile to think about this new regime of polymers that we haven't talked about before. All right. And so as the counter ions, remember these are the counter ions. And the negative charges are ions in the repeat unit. The charges on the backbone are less shielded from each other, and so you get more repulsion, and that coil expands. And just as we talked, and just as we talked about, if we add NaCl or other electrolyte to solution, we get more ion pairing, and the polymer chain is more coiled. Great. And we'll talk more about this. So I don't show lots of videos in this class, but I make an exception for this one, if I can find it. There we go. So this is sodium polyacrylate. When you can buy sodium polyacrylate off of Amazon or anywhere else, it's like a white powder. It looks like little styrofoam beads or something like that, but it does some pretty awesome stuff. See if this works. All right. We've got YouTube music. You can listen to that if you want. So that's sodium polyacrylate powder that's mostly dry. So if you've ever cracked open a diaper and there's little beads in there, or it looks like powder along with the cellulose, it's this stuff. And they're going to add water to it. You can see those teeny little beads. We don't need the reggae music, although I do enjoy it. Thank you, YouTube. So you can see how much water they're putting in there. And it turns out that these polymers can uptake 1,000 times their weight in water because of this ionic effect, right? Salts really love water, and so these polymers can absorb a heck of a lot of it. Or if you ever go to a hotel and they have lots of indoor plants and you look at one of the planters, sometimes you see this stuff in there, that like gel stuff that they put in indoor plants. That's this polymer because it retains a lot of water. Yeah. That's right. This is the still absorbent. It turns out that at Penn State, they invented, Mike Chung, who's in MATSE, invented what's called Petrogel that does exactly the same thing with oil. So rather than super absorbent polymers for water, he made super absorbent polymers for oil to clean up oil spills and other things like that. And it turns out it was just a special form of polyethylene, because polyethylene really loves oil because its solubility parameter is very close. So this is a really interesting, useful technology. All right, and I think that is it. Great, okay, very exciting. And
why doesn't every home in the US have solar panels?
and there's lots of other
The number one reason is
YouTube
not about
videos to
sunlight,
check out, so
weather, or even politics.
there we go. Okay, so clicker question. If you add sodium chloride to an aqueous solution of sodium polyacrylate, so aqueous solution of sodium polyacrylate that's already in water, right? How would the polymer conformation change? Nothing would change. The polymer would be more extended, swelled up, or the polymer would shrink. Great, right in there. Of course, everyone said the polymer would shrink or become more coiled because the added salt pairs up those ions. It turns out that this can get pretty complicated. And when I was an intern at Kimberly-Clark, when I was an undergraduate chemical engineer at Michigan Tech, they were inventing super absorbent polymers that little kids could swim in the pool with. So pools have a much lower salt content. This is back in the day of chlorinated pools, not saltwater pools. But pools have a much lower salt content than urine. And so they wanted the diaper to work, you know, when the kid peed in it, but they didn't want the diaper to completely blow up in the pool. So they were working on these types of polymers to get polymers that swell in salt water and polymers that don't swell in regular water. So the opposite effect of this sodium polyacrylate. And that's, you know, sort of swimmy diapers you used to, when I was a kid, you put like this plastic bag around a diaper to prevent water from getting in. Now swimmy diapers can get wet and they don't take up water unless the kid pees in it. Very interesting technology. And like I said, people like Kimberly Clark are dead serious about it because it's billions of dollars. All right. Any questions, any comments on that? Okay. If someone's working on their honors essays for this class, you could easily do one on superabsorbent polymers because there's just lots of awesome stuff to think about. All right. So what's the difference between polyelectrolyte or your garden variety electrolyte and an acid or base? So you know what acids are, you know what bases are, you know what electrolytes are. What's the difference between them? Yeah, so pH, acids and bases, we talk about pH. And what does pH describe? Concentration of protons, right? And so we can do similar things. This is a pH neutral or pH 7 electrolyte because it's a salt, right? You take sodium chloride and put it in water, the pH of that water doesn't change. But we can easily change the concentration of protons or hydroxide, however you want to think about it, in water by changing the pH. And if we have a pH responsive unit in our polymer, like acrylic acid, so you notice that this is very, very similar to sodium acrylate, right? So sodium acrylate has an sodium on there, and acrylic acid has a carboxylic acid built into it, right? So this is carboxylate group, and this is going to be our acidic proton. And so if you take an acid and you put it in high pH, what does high pH mean? What's the definition of high pH? Basic. Is there a high concentration of protons in a basic solution or a low concentration? Low concentration of protons at high pH, which means that acids are going to dissociate, right? So if there's a low concentration of protons in solution, that means the H on here is going to float away. So acids dissociate at higher pHs. If I go to really low pH, what's the definition of low pH? What's happening in solution? Lots of protons in solution. And if I have excess protons around an acid, I'm going to force a proton onto that acidic group. So this is the nature of pKa and pKb, right? What pH do those protons dissociate from the acid? We're not going to go that far, but we can talk about pH responsive gels in the exact same way that we talked about, let's say, a salt responsive polymer. And there's nothing fancy about pH responsive versus salt responsive. We just have to remember this idea of high pH is low proton concentration and low pH is high concentration of protons, and how that drives dissociation. And so what happens at low pH, we have excess H plus in solution. And it's going to force ion pairing of this carboxylic acid. Does everyone get that? Great. And the polymer is neutral, so it's going to coil up. We have neutral polymer. And it's going to be coiled. As we go to high pH, we've got low H plus concentration in solution. And if we have low proton concentration in solution, that means that this proton is free to dissociate. And so now we have a dissociated polyelectrolyte. In essence, we've got like charge repulsion along the backbone, and we have expanded coil due to negative charges repulsing each other. And that's really cool because we can see that in these micrographs. So this is a little ruler with some millimeter markers. This is a pH gel that we take this acrylic acid and this crosslinker. So the degree of functionality of this thing is 4, right? The degree of functionality of this thing is 2. So we put this together and we make a polymer gel or a solid piece of polymer when we polymerize that. And then we can put it in water and we can change the size of that polymer depending on what we're doing with the pH. And this is really cool because all we're doing is we're changing the ion pairing, and that's causing a physical change in the size of whatever thing we're interested in. In this case, it's just this disc. So, you know, it's a little bit esoteric to say, okay, you know, I'm interested in this polymer coiling and uncoiling. Okay, that's great. Why are polymer coils in solution important? But there's a lot of interesting biomedical technology that leverages this pH responsive idea. We already talked about super absorbent polymers, but people are interested in using pH responsive polymers for biomedical diagnostics or for sensors or for actuation, where instead of having a motor and a lever and doing electrical actuation, you can do chemical actuation, or you can get polymers to respond to their chemical environment. So there's a whole host of different environmentally responsive or pH responsive or responsive polymers in general to light, heat, chemical gradients, other things like that. So now the polymers are moving depending on what chemistry we put inside them and what stimulus they see. Questions, comments on that? All right, so this is really interesting, and it's useful if you sort of start with the basics of what's happening with the polymer chain. What chemistry in the polymer do you need to make it salt responsive or pH responsive? And then what might happen depending on whether you're pairing ions or unpairing ions. And the thing to remember is unpaired ions, the coil stretches out, things can dissociate, that's good. And when you have paired ionic systems, either at low pH, or you could have a base responsive polymer if you really wanted to. Amines are base responsive because they can be protonated. And so you just have to figure out which way the interaction is going. But when you have paired ions, the polymer coil shrinks. Questions, comments on that? All right, and I think there's some things, yeah, to summary. Okay, so you can read those things, and I'll ask you some questions on the next homework, PLAs, etc., about polyelectrolytes. All right, the next thing that we want to talk about is characterization. So we have some idea of now polymer sizes in solution. We've talked about conformation. You know, we've drawn a lot of polymers on the board or on the PowerPoint slides. Now we want to figure out, how do you know what you have? You know, we've talked about a lot of numbers: molecular weight, chemical structure. We've talked about TG, we've talked about TM, and we've talked about all these properties, but we actually haven't talked about any measurements of, if you have a polymer, if you walk by a polymer on a street, how do you characterize that polymer? How do you figure out what that polymer is? And so here's our polymer unknown. And so if we're interested in the molar mass dispersion or distribution or the dispersity, in this class, we're going to learn about something called size exclusion chromatography. And so at low molecular weight, if we have a polymer with low molecular weight, is the coil big or small relatively? Small, right? We don't have many monomer units, coil small. If we have high molecular weight polymer, the coil gets bigger. And so size exclusion chromatography is going to tell us what size coils we have in solution. And so we're going to learn about that. And if we calibrate that technique correctly, we can get molecular weight directly from figuring out how big the coil size is. What does chromatography mean? Does anyone know? If I say we're going to do chromatography, what pops into your head?
In the water.
Yeah, you put some stuff in, but what physically are you doing?
You're measuring the transfer of a chemical through a solute.
That's right. Well, you're measuring the transfer of chemicals through some sort of bed, some sort of packed bed, or some sort of porous medium. And the interactions, whether it's size or chemistry or polarity, the interactions between the stationary medium and what you're trying to separate, you basically get separation as you go further and further down this column. So when you do chromatography, old school with the column, you pour stuff in the top and it separates down below, and then you can collect those different fractions. Did you guys do TLC in your organic chemistry lab? What is that? What does TLC mean in organic chemistry?
Thin layer chromatography.
Thin layer chromatography. So that's a glass slide, and what's that white stuff sitting on top of the glass slide? Silica sort of all stuck together, and you put a drop of your unknown at the top. And then what did you do in TLC? So you put that drop on, you wait a couple minutes, or you put it in a solvent. What did you see? You see those bands, right? That's chromatography in a thin layer. Now we have column chromatography. We've got other fancy types of chromatography, but all chromatography means is that we're separating things, and then we can count what we separated. And so size exclusion chromatography is we're just separating these coils by size. And it turns out when you have a molar mass distribution, you've got a lot of coils of different size, and so size exclusion chromatography, you can separate it. All right. Let's see. We have osmometry and N-group analysis. So we can get molecular weight and also chi interaction parameter from osmometry. We're going to talk a little bit about that. What types of spectroscopy do you know about? Like when I say we're going to do some spectroscopy, what's a technique or a name that pops into your head? X-ray is not spectroscopy. Well, you can do X-ray spectroscopy. That gives you different elements, but that's more for inorganic characterization. What optical will give you optical phenomena? That's right. But what's the spectroscopy that you learned about in organic chemistry?
Mass spectroscopy.
Mass spec. What else? What's an easy one? NMR. FTIR. And what do NMR and FTIR tell you about? Mass spec obviously tells you about the mass of different things flying through your spectrometer. What do NMR and FTIR tell you about? Yes.
Functional groups.
Chemical functional groups, right? So that's really important. When you have polystyrene, how do you know what the functional groups are? You take it to the NMR or you take it to the FTIR and you can fingerprint that. So NMR and FTIR are key techniques for figuring out what functional groups are in the polymer. We're going to talk about thermal transitions a little bit, and then in future classes, you'll talk about light scattering and diffraction and other things like that. But it's really important to think about this slide and think about what the technique is measuring and why that matters to all of the polymer stuff that we've talked about so far. Any questions? Yes.
Light scattering and refraction, called tacticity.
Not usually unless you do circular dichroism or something like that. If you have polarized light, you can talk about tacticity. We'll talk about that as we go further. All right, see you on, what day is it today? Wednesday? Yeah, see you on Friday. All right.